Hi everyone. I wanted to step in here and give a little talk about cycle notation in the symmetric groups. This is covered in section 7.5 of Hungerford's textbook on abstract algebra in the third edition of the book. In section 7.5 he talks about this, but I just want to give a quick overview of what cycle notation is about and why we want to use it, what it's good for. So to do that, I've kind of made up an example here. I've written down sort of our two-line notation for an element. This is actually going to be an element of S12, right? So I wanted to make a fairly big example. Remember, in the two-line notation, the top row just shows the domain from 1 through 12. And the bottom row shows the range. And you can just imagine the function going from the top line to the bottom line. So 1 maps to 4, 2 maps to 6, 3 maps to 1, and so on. And so this is, of course, one way to represent the elements of the symmetric group. Remember that there will be n factorial of these different permutations, right? Because there will be n factorial ways of assigning the second row of this two-line notation. But we very quickly start to realize that this notation has some drawbacks. The operation in the symmetric group is composition of functions, and when you're composing functions together using the two-line notation, it turns out to be quite cumbersome. So it turns out there's a nicer way to do it, and it's called cycle notation. And I'm going to show you how to do the cycle notation right now. Just for this element sigma, this example that's up here, and I think you'll get the idea. Okay? What you need to do for cycle notation is we're going to just draw one line of different cycles. And you can start with whatever cycle, whatever number you want. Usually, for lack of a better reason, I will usually just start with the very first number in my set, which would be 1. And I look at where 1 gets mapped by sigma, and I simply write that down next. And so you can, instead of sort of thinking of the function as going from top to bottom, now it's just kind of moving from left to right. Okay? So it's like 1 mapping to 4 here. Okay? And then after the 4, what I do is I do the same thing again. I figure out, well, where does 4 get mapped? So I'm going to skip over the 2 and the 3, and I'm going to say, well, 4 gets mapped to 10. Okay? And then I can say, well, where does 10 get mapped? 10 gets mapped to 3. I keep going like this. Now 3 gets mapped back to 1, and I have to remember that 1 was where I started in this cycle. So I'm going to close that cycle right there. Okay? So the first cycle is just 1 goes to 4, goes to 10, goes to 3, goes back to 1. Okay? Now, there are a lot of numbers that we haven't written down yet, so we need to start a new cycle. And again, we can start with any number that we want that we haven't used yet. So obviously I'm not going to start with a 1, 4, 10, or 3, but you know, the next number sort of in order of numbers would be 2. And I can start with 2, and I can say, all right, starting from 2, 2 gets mapped to 6. When I look over here at what 6 does, it goes right back to 2 again. So that cycle is already closed. Okay, so by the way, this first cycle is called a 4 cycle. The second cycle, a cycle of length 2 is, of course, could be called a 2 cycle. It's also called, a lot of times, a transposition. A 2 cycle or a transposition. Okay? Now, what's the next number that we haven't used yet? We've used 1, 2, 3, 4. It looks like it's 5, right? So I'll start with 5. And then I'm going to notice that 5 gets mapped to 7. 7 gets mapped to 8. And 8 goes back to 5 again. So I close my cycle, and this time I have a 3 cycle. Okay? Notice that the next number in my list would be 9, and that number is just fixed. So it's a cycle of length 1. And the next number that I haven't seen yet is 11, and I see that 11 goes to 12, and then 12 goes back to 11, so I get another transposition here. Okay, so this would be the cycle notation for sigma. Let me make a a couple of comments about this. First of all, you don't see any of these numbers more than one time, right? Every number from 1 through 12 can only be in one cycle after you've done this procedure, right? Another thing to notice is that I don't have to start, for example, this first cycle at 1. I can choose any point here. If I was writing this down, I could write it differently. I could start with 10, right? And of course 10 still goes to 3, which still goes to 1, which still goes to 4, which still goes back to 10, right? Nothing wrong with doing that. I can do the same thing here, for example. I could do 8 to 5 to 7. As long as I'm writing the numbers in the same order, right? Sort of from left to right. Remember, you're kind of moving to the right before cycling back, okay? So these two cycle notation expressions that I've got on the board are exactly the same, right? I mean, they look different, but they represent the same sigma. Okay, these are equal. The other thing I want to mention is that when you have a singleton in a cycle, you can just as well omit it. Okay, so now the 9 does not appear anymore. And there's nothing wrong with that. If I saw this cycle sigma like this, I would just assume that any missing numbers are simply fixed, right? 9 goes to 9. So if we don't see that number 9 down here, that's not alarming to us. It just means that we should assume that that number is fixed. Okay? Now, why do I like having this cycle notation down here so much? Well, it turns out it makes things a lot easier to apply the operation in Sn. Remember that Sn is a group under composition. So, you have composition of functions. Let's imagine for a minute that I wanted to know what sigma squared was, right? I want to multiply sigma by itself. Well, if I use the original two-line notation, I'll have to trace through, this whole big notation in quite a bit of detail. But if I've already got this notation down here, this cycle notation written down, it becomes much easier. See, for example, I can say, well, you know what? I'm going to start again with 1. Okay, so maybe we can go back to the first. Again, it doesn't matter which of these formulations we use. Let's just use the first one here. We start with 1 and we imagine doing sigma twice. We're squaring sigma. Well, if I move 2 spaces to the right here, 1 ends up at 10. Right? And then I can look at 10 and I can say, well, if I go 2 spaces forward, if I apply sigma twice, starting from 10, I'll first go to 3 and then back to 1 again. Right? Okay. Similarly, if I started instead at 4, and I went if I hop 2 steps to the right, I end up at 3, and if I hop 2 more steps to the right, I'm back to 4 again. Right? Let's suppose I started here with 2. If I apply sigma twice, well, it's first going to go to 6, and then it's going to go right back to 2 again. Okay, so 2 gets fixed, and similarly, 6 gets fixed. Okay? What about over here? What's going to happen? Well, if I start with 5 and I go 2 steps to the right, I'll end up at 8. If I start at 8 and I go 2 steps along my cycle, I end up at 7. And if I start at 7 and I go 2 steps along my cycle, I end up at 5. Okay? The 9 is already fixed. And the 11 and the 12, when I square sigma, they also get fixed. So you have some numbers here that, of course, you could just omit now. Right? And so this product would be your answer for sigma squared. Okay? And it consists of, in this case, 3 disjoint cycles. Disjoint meaning that you don't see the same numbers more than once. Right? So the 1 and the 10 don't occur here. The 3 and the 4 don't occur here. 5, 8, and 7 don't occur here. Right? Different numbers in different cycles. Now, one of the things that's really nice about this is it gives you a quick way of finding the order of sigma. Because we're talking about what is the first power of sigma that gives me E. Now keep in mind that in the cycle notation, E would just be the element that fixes all of the numbers. So you would have 12 singletons, right? 12 cycles that just have one thing in them. So the question is, well, what would it take? How many powers of sigma would it take to achieve that? Well, if you look at this first cycle in sigma, you see that in order for 1 to get mapped to 1, you're going to have to hop forward 4 times. 4 steps, right? And if you do that, the other numbers in that cycle will also end up being fixed. Because it's a cycle of length 4, if you apply sigma to itself 4 times, that cycle becomes, the 4th power of this cycle just becomes, 1, 3, 4, and 10 as singletons, right? So every 4 powers of sigma will sort of cancel out the first cycle. And by that same reasoning, every 2nd power of a transposition will get canceled out. Every 3rd power of a 3 cycle will get canceled out, and so on. So the question becomes, well, when will all of the cycles simultaneously be canceled out? Every 4th time, every 2nd time, every 3rd time? Turns out the answer is you take the least common multiple of the cycle lengths of sigma. Okay, so here's a nice little fact. The order of sigma is the LCM of the cycle lengths of sigma. Okay. All right. Now, so that's one very nice thing to be able to do with the cycle notation. Let me give you another one. Suppose that I came along with another element. I'm going to call this one tau. And suppose that I have an element that sends 1 to, let me just get this, 1 goes to 7, 2 goes to 1, 3 goes to 5, 4 goes to 2, 5 goes back to 3, 6 gets fixed, 7 goes to 4, 8 goes to 12, 9 goes to 10, 10 goes to 11, and 12 goes to 9. Let's suppose we took sigma. Let's imagine that I wanted to work out what sigma times tau is. Let's suppose I just want to do this multiplication. Doing it, of course we do this from right to left, right? Okay. Doing this from the 2-line notation is going to be a bit cumbersome. I'm going to say, well, 1 goes to 7 in tau, and then 7 goes to 8, so that would mean that 1 goes to 8, right? And I would have to do 12 more sort of mental calculations that are like that. Well, turns out that if you, instead of doing that, if you just do the cycle notation, so let's write down sigma. Sigma is on the left here. 1, 4, 10, 3, and then 2, 6, and then 5, 7, 8. I won't write down the 9, just write down 11 and 12. And now let's work out the cycle notation of tau, and I'm going to just continue this string here. So 1 goes to 7, then 7 goes to 4, 4 goes to 2, 2 goes to 1, and then 3 and 5 form a transposition. 6 gets fixed, so I won't write it down. 8 goes to 12, which goes to 9, which goes to 10, which goes to 11. Whoops, I forgot to write down 11. Let's make another number in here. What am I missing here? 11 goes to 8. Okay, so let's make 11 go to 8. There we go. Okay, so suppose we have something like that. Now, this is not simplified yet. And that's because I see the same numbers in more than one cycle. There's an 8 right there and right there, right? There's a 2 right here and right here. So this is not a simplified expression. And for example, if I wanted to know the order of sigma tau, I would not be allowed to just take the LCM of these cycle lengths, because this has not been simplified yet. Okay, so what I'm going to do is simplify that now. Okay, so I'm going to come up here, we're going to erase our sigma. In fact, we can erase all of this stuff at this point. You can always pause and rewind, of course, if you need to. But what I want to do right now is just simplify this. And it is still true that we multiply from right to left. So when I'm working out the cycle notation simplification of sigma tau, I'm going to, pick my number that I want to start with here. I usually like to start with 1. Okay, not that you have to. You can start with any number, but I'll just start with 1. I say, well, there's no 1 right here. There's no 1 here. There is a 1 right here. And in this cycle, the 1 maps to 7. So I'm going to remember that for a moment. So imagine that 1 has been mapped to 7, and now we're continuing to move to the left. There's no 7 here. But here, the 7 gets pushed to 8. Okay, so now we're at 8, right? We go to the next cycle. There's no 8 here. There's no 8 here. So we're done, right? 1 goes to 8. This is how you have to think about it. Let's try this again. Let's start with 8 now. Okay, we take the last number that we wrote down, and we're going to start with that. Way over here on the far right, notice that 8 goes to 12. So now I move to the left and I look for a 12. There's no 12 here. Just means that this transposition fixes 12. So it's still 12. This 4 cycle fixes 12. There's no 12 there, so it's going to leave 12 alone. But here, the 12 is going to move to 11. Okay? And I keep going to the left now with 11. There's no 11 here, no 11 here, and no 11 here. So I'm done with an 11 there. Okay? Now let's start over with 11. We go way back to the far right. 11 gets mapped to 8. There's nothing, no 8 here, there's no 8 here, there's no 8 here. Here the 8 moves to 5. Okay, so we have to put a 5 there. By the way, we should not ever be writing the same number twice up here, right? They should always be different. Starting from 5, there's no 5 over here at the far right, but here the 5 is going to move to 3. There's no 3 here, there's no 3 here, there's no 3 here, there's no 3 here, but here a 3 goes to 1. Aha! That's the end of that cycle, because we ended at 1, which is where the cycle started from. Okay? Now let's start over with our next favorite number. So I'll pick 2, because I haven't used a 2 yet. Alright, so there's no 2 here, there's no 2 here. Here's a 2, and it maps to 1, right? Go like this, it maps to 1. So now we look for the 1. There's no 1 here, there's no 1 here, there's no 1 here, but here the 1 maps to 4. Okay, so that's where things finish up, is with 4. Okay, let's see if we can go a little faster with this. Where does 4 get mapped to? If you want to, put me on pause for a minute, see if you can fill out the rest of this element, and then we can, then you can watch and see if we've done it correctly. So here, for example, the 4 goes to 2, and then 2 goes to 6. So I ended up at 6. Let's start over with 6. There's no 6 over there, but there is a 6 right here, and it's going to 2. It's the end of that cycle. Okay? Let's pick the next number that we haven't used yet. How about 3? 3 moves to 5 right here, and then 5 moves to 7. So 3 moves to 7. Okay? Starting with 7, what happens? Well, 7 goes to 4, and then 4 goes to 10. I'll put 10 there. Okay, now where does 10 get mapped? Well, it starts off getting mapped to 11, but then 11 gets mapped to 12. So I'm going to put 12 there. Okay, what about 12? 12 maps to 9, and I don't see any other 9, so that means we stop with 9 right there. 12 going to 9. Okay, let's keep going. Actually, I think we've got 4 plus 3 plus 5. We've already got 12 numbers, so there better not be any other numbers. Let's see. 9, therefore, should go back to 3. Let's just check that. 9 goes to 10, and then 10 goes to 3. It absolutely works. Okay, so there's the final answer. How do you know that this is not the right answer and this is? Well, it's because this one consists of disjoint cycles. There's no number appearing in more than one place up here, right? Whereas down here, this is unsimplified because I see the same numbers in different cycles, right? That's kind of how you know that. So if I wanted to know the order of sigma times tau, I would take the LCM of, this cycle has length 4, this has length 3, and this has length 5. Now the LCM of 3, 4, and 5 is actually 60. So this is an element of order 60. Okay, which would have been very hard to just get from this representation down here. Okay. I guess the LCM of these cycle lengths would have come out in this case to be 60, but that's really just a coincidence. You cannot figure out the order of an element when it's not simplified yet. To be careful about that. For example, if I had the element 1, 2 times 1, 3, these are two cycles, but it's not been simplified yet, right? I have to simplify it first by doing my right to left multiplication. Let's see, I'll start with 1. 1 goes to 3, and then there's no 3 here, so I just stop at 3. 3 goes to 1, but then 1 goes to 2, so 3 goes to 2. And then 2 goes back to 1. So this is a calculation, and notice that the order of this element is actually 3, because it's a single 3 cycle. So despite the fact that the cycles were both length 2, the LCM of 2 and 2 is not giving you the correct order, right? The correct order comes once you simplify that product into a disjoint cycle and you look at the length of that cycle. Okay, so just understanding the different cycle types that you can have is a really powerful way to study the symmetric group. For example, you know, S5, I mean, this is a pretty big group. It has 120 elements, right? 5 factorial. But if I only wanted to think about what are the different kinds of cycles that I could have, it's actually a lot easier, right? I could have a single cycle of length 5, right? Something where you have 5 numbers put together like that. Or I could have a single cycle of length 4 where one of the numbers was fixed and therefore didn't get written down, right? Or I could have a cycle of length 3, something like that, where 2 of the numbers are fixed. Or I could have a cycle of length 3 and then a disjoint transposition to that. So you could have something of that form. And what else could I have? Let's see, I could have a 2 cycle, which is just a transposition. Or I could have 2 of those, right? Or I could have an identity element, E, where you don't really have any cycles at all. And I think that that's about it. We get about 7 different cycle types. A good little exercise for you might be, if you want a sort of a combinatorics problem, figure out how many of each type of cycle notation that you have. In total, you should have 120 elements here. So it would be kind of fun to just count them up and make sure that that really is correct. But this is a more manageable way to study the symmetric group, is to just write down the cycle types for the symmetric group and analyze each type sort of on a one-on-one basis. I mean, we already know, for example, that everything of this type will have order 5. Everything of this type will have order 4. Everything of this type will have order 3. Everything of this type will have order 6, because the LCM of 3 and 2 is 6. Everything of this cycle type will have order 2. Same here, order 2, right? And of course the identity element has order 1. So you know the orders of all these different types of cycles immediately, right? And so we're going to see that there are other reasons that I haven't gotten into yet for why cycle types are really useful and really important to study. I hope that this has made some sense. I hope that you're enjoying this stuff. If there's anything you have any questions about, by all means, feel free to ask me. I'll do everything I can to clear things up and get you guys back on track. Thanks a lot for your time, and I'll see you soon.